Hi everyone, my name is Clayton Barham and today's topic is high-resolution image synthesis using conditional GANs, as well as semantic object manipulation. So first we're going to talk a bit about the motivation behind this paper, as well as the pix-to-pix network that was used as the basis for this model. We're going to talk about some of the primary steps the authors took to improve the photorealism and resolution that they could produce with their output, along with some of the additional steps taken to improve output and to enable object manipulation. Finally, we're going to talk about the experiments and results that the authors performed, as well as a showcase of the object manipulation that we've been talking about. Motivation. So the primary motivation of this paper is to synthesize high-resolution images using conditional GANs with semantic label maps as input. The previous method that the authors build upon is the pix-to-pix network. That is an image-to-image translation network using conditional GANs, which were talked about a little bit by Bruce in the last presentation. It works well on low-resolution images, 256 by 256, but it has difficulty with high-resolution images like 2048 by 1024. It produces blurry images with some visual artifacting. An improvement that the authors discuss is the perceptual loss function. However, while that is capable of producing high-resolution images, it has issues with lack of detail and repeated patterns. The authors hope to address both of those issues. In addition, they want to allow objects in the image to be added, removed, or edited in an intuitive, easy way, as opposed to manually editing a semantic label map, which would be cumbersome. So, starting a little bit with pix-to-pix. Pix-to-pix is the state-of-the-art conditional GAN framework. It uses a UNet architecture for the generator, a patch-based, fully convolutional network for the discriminator, and a traditional GAN loss function. Here are some examples of the semantic label maps that would be taken as input by pix-to-pix. Each pixel color corresponds to a different class that the pixel belongs to. And here are the outputs. As you can see, the outputs are blurry, indistinct. We have some visual artifacting at various points in both of these images. This is what happens when you take the pix-to-pix network as is and try to run it at higher resolutions than it was intended for. The authors hope to address this problem by improving the generator architecture to use what they call a coarse-defined generator, by improving the discriminator architecture to use a multi-scale discriminator, and by improving the loss function to stabilize training. So starting with the generator, the coarse-defined generator consists of two components. G1 is the global generator. It has three components to its architecture: a front end, some residual blocks, and a back end. This is a standard convolutional network architecture that's performed well in a variety of GAN applications. G1 takes an input that is a quarter of the desired resolution, half on each dimension. So in this case, 1024 by 512.
So that's a semantic segmentation.
Yes, this is a semantic label map. Passes it through G1 and outputs an image that is, again, that same size, a quarter of the total resolution. The reason for shrinking the size of this image is that by shrinking the size of that image, the same kernel maps simulate a higher receptive field. In order to ensure a global consistency, as the global generator is supposed to, it needs a large receptive field that can check a large amount of the picture. There are two ways to do that. Either use a large kernel map, which means a lot of neurons to train, or shrink the image. That way the same size kernel map simulates a larger receptive field. The authors went with that approach to save training time and memory space. In addition to G1, we also have G2, the local refiner. G2 takes input and produces output that is of the desired size. And like G1, it takes a semantic label map as input and produces an image as output. The G1 is sandwiched in between the front end and the residual blocks of G2. The semantic label map input is given as input to G2. It is also downsampled and given to G1. It runs through the front end of G2 and the whole of G1 independently, after which the output of G2's front end and the final feature map produced by G1 are summed together element-wise. Because the front end of G2 downsamples the image size, these are the same size. As a result, we get a feature map that integrates the global and local information that's been obtained so far. That information is given to the residual blocks of G2 to be processed and then blown up into the final result.
So G2 has actually two parts, this part and this part, and they're put together like this to explain them. And the input to G2 is the highest resolution, right?
Yeah, the input to G2 is the 2048 by 1024 input, or the 2048 by 1024 semantic label map that's of the desired size. Yes, and G1 is sandwiched in between parts of G2. All right. In addition to the coarse-defined generator, which operates at multiple scales, we also have discriminators that operate at multiple scales. The architecture of the discriminator network itself remains unchanged from pix to pix. It's a patch-based, fully convolutional network. What changes is that we don't use one discriminator. We use multiple discriminators that, again, operate at different scales. So D1 here takes input labels, an image, real or synthesized, and some additional information that we'll see later, and takes that at the desired resolution, 2048 by 1024. For D2, we downsample that by a factor of 2, so this is 1024 by 512. And for D3, we downsample that again by a factor of 4 to 512 by 256. The reasoning behind this is the same as it was with the generator. By shrinking the image size, the effective receptive field grows for D2 and D3. So D1 checks for fine detail, while D2 and D3 check for larger global consistency. The authors found that when they used a single discriminator, just D1, while the details were good, they had repeated patterns because the convolution kernels would check this instance of the pattern is appropriately detailed, this instance is appropriately detailed, but there was no global checker saying, hey, there's 2 of this pattern and there should only be 1. With D2 and D3, we have intermediate and global consistency checking that enables catching that kind of pattern. I do not believe that the authors explained why they used 3 levels of detail here as opposed to only 2 in the generator, but that is a design choice that they made. Finally, in addition to the generator and discriminator architectures, we also have a change to the loss function. This is the traditional GAN loss function that we've seen plenty of times before, the min-max game between the generator and the discriminator.
So what is the S and what is X?
Okay, S is the semantic label map, X is the ground truth image, and G of S is the synthesized image. Here we have the author's contribution, the feature matching loss. As you can see, it's the L1 norm of the difference between the feature value obtained for the ground truth image and the feature value obtained for the synthesized image, weighted by this factor n. The feature values used here, dik, this is the input vector taken to the ith layer of the kth discriminator. So we have 3 discriminators, each of which has several layers. So the input to layer 1 of discriminator 1 is D11. The input to the 5th layer of discriminator 3 is D53. And so for each layer of each discriminator, we take the input values that we obtained when we gave it the semantic label map and the real image, and the input values that that layer received when that discriminator was given the semantic label map and the generated image, and we take the L1 norm of that difference to determine how different the activations were.
And what is the NI?
The NI is the number of units in that input, so it's weighted by the size of the input. The reasoning behind this kind of loss function is that in order to stabilize training, in addition to requiring that just the output looks realistic, it's also required to generate natural-looking statistics at different layers of the discriminators at different scales because of having multiple discriminators.
So the features should look the same.
Yes. Yes, in order to help further constrain high-resolution training, it needs basically more guardrails. And here we see the perceptual loss that the authors mentioned earlier. As you can see, it takes a very similar form to the feature matching loss. That's because feature matching loss was based on perceptual loss. The difference is what we're using as the feature value. Instead of using inputs to layers of discriminators, we're taking the output, we're taking inputs to layers of a pre-trained VGG network. So here, fi of x is the input to layer I of the VGG network given the ground truth. Here, fi g of s is the input to layer I of that VGG network given the synthesized image. So you can take the L1 norm, normalize by the size of that input, and sum it up. The reason that the authors moved away from perceptual loss and towards their feature matching loss is that pre-trained networks like VGG aren't available for all applications. But if you're doing a GAN process, you always have the discriminator to look at. In the experimental portion, the authors do perform experiments with and without the perceptual loss, in addition to the feature matching loss. And they find that it does affect the results somewhat.
Which makes sense, right? Because it's better to use the feature matching.
And here we have the total loss function used by the authors of this paper, combining the GAN loss and the feature matching loss. VGG is not the perceptual loss is not included in this equation because it's an optional feature. The basic loss function that they use for all of their networks always included GAN loss and feature matching loss. In addition, there was an optional component of the perceptual loss, but this is the basic. And here we sum up the feature matching loss across each discriminator. The GAN loss, the same thing, the min-max game, the contributions of the three discriminators are combined together when playing the min-max game. And this lambda value controls the importance of the feature matching loss. In their experiments, they use a lambda value of 10, which places a high importance on this feature matching loss.
So in this one, the reason they don't have separate loss for G1 and G2 because it's the way they combine it.
Yeah.
At the end, there's just one output.
Yeah, they're combined together to produce one output image at the end. Whereas the discriminators, they each independently produce their own predictions. So they have their contributions have to be summed together to determine how well did you fool all three of them. All right. In addition to those primary contributions to the generator, discriminator, and loss functions, the authors also improved the results and enable object editing by using what are called instance-level semantic label maps. So in a traditional semantic label map, the color of the pixel corresponds to class, but there's no concept of individual object. For example, this picture is a bunch of cars parked on the street. This right here, these pixels are all of class car, but there's no distinction between individuals. This could be 10 cars parked end to end. This could be a stretch limo. The image doesn't tell you which that is, and as a result, the conditional GAN doesn't care. It just produces pixels of class car for that block. What an instance-level semantic label map does is, in addition to class information, it also contains instance information. So here, this would be class car instance 0, class car instance 1, class car instance 2, and so on. From that information, the authors extract what they call a boundary map. For every pixel of the boundary map, it's colored black if the pixel is the same instance and class as all of its neighbors, and white if one of its neighbors is different. So here in the cars, these black pixels, these all belong to car 0, so they're all the same color. Right here, we hit the boundary between car 0 and car 1. Since these pixels are now different colors than some of their neighbors, they get colored white. Same thing here where we have a boundary between the car and the road. This information is concatenated with the semantic label map and the input image, either real or synthesized to the discriminator as well as the input information to the generator. So the generator is getting a semantic label map and a boundary map. The discriminator is getting a semantic label map, an image, and a boundary map.
So the standard semantic labelings, they don't have the boundary. So it seems for this paper they did that additional.
Yeah, they made use of that additional information that was available through object level segmentation, in addition to just class level segmentation. The reasoning for including that, in addition to something we'll see in the next slide, when you do not make use of that boundary information, it produces one large object of class car, which does not always have a distinct boundary. Whereas over here, when we do include the distinction between different cars, we see crisper boundaries. This helps reduce some of the visual artifacting we see, as well as the fact that the object level information gets used in the next slide. Because in addition to using that for just boundary mapping, they also use it to learn instance level feature embeddings. These are used for the purpose of object manipulation. The feature embeddings are low dimensional vectors, 3 dimensions in the case of the experiments the authors ran. The way these are determined and used, we take our original image first, and we feed that to an encoder-decoder network. The encoder-decoder network learns a feature value for each pixel. There is an average pooling layer at the end of the encoder-decoder network that performs instance-wise average pooling. So for every pixel that belongs to the same instance of the same class, so for every pixel belonging to car 0, for example, it will average the values together so that they all have the same value. So after this average pooling layer, we now have a feature map image here, or we have a feature map where every pixel belonging to car 0 now has the same value.
So in that, there is a feature, or is just a flag that this is car, or this is car 1 or car 2?
It's a 3-dimensional feature vector.
Feature vector.
Yeah, it's a three-dimensional vector, continuous valued elements. And every instance of every object has a unique value of that feature vector.
Okay, so yeah, go ahead.
That feature map is concatenated with the inputs to the generator and discriminator. So the generator is now obtaining a semantic label map, a boundary map, and a feature map. And the discriminator is now taking a semantic label map, an image, a boundary map, and a feature map. The generator architecture is reproduced there for convenience. And from that, we obtain our generated image. This is useful because all pixels belonging to the same object have the same value. So if you substitute the value of all of those pixels, you could change that object. For example, if car 0 was like a white Honda and you wanted a blue Versa, you would swap in the pixel value, the feature values mapping to blue Versa into the pixels for white Honda. And when you ran that image to the generator, there would be a blue Versa there instead of a white Honda if the original image had a white Honda.
So this feature, I mean, first this is pretty small feature vector, 3 dimension.
Yeah.
But then they use this autoencoder to get the feature pooling. But can you do this same thing, like since they have a boundary of the object anyways, right? So they can just put any feature vector as far as they are different for different objects.
They could do that, assign just arbitrary labels, but they wanted, the reason they use the encoder-decoder network, we'll see that a little bit more in the next slide, is that they wanted to map these into an embedding space where similar objects would be close to each other.
Oh, okay.
Because, well, first we're going to just have a quick summary of what I talked about. The encoder-decoder network learns feature values. Those are averaged instance-wise to obtain standardized feature values for a given object. And those are concatenated with the input to the generator and discriminator.
So on this thing, like if you assign the same code to each, the same code to the same class, then you can cluster those very easily, right?
Yep, that
will be easier than the features may vary a little bit. So yeah, anyway, so code, then we can come back to that.
Yeah, so the reason they wanted to map these features into an embedding space as opposed to just picking arbitrary labels is so they could perform k-means clustering on a per class basis. So after we've run this encoder-decoder network on every image, we've now obtained a standardized feature vector value for every object of every class. So on a per class basis, we perform k-means clustering. So for example, if we're talking about class road, and we do k-means clustering on all of the road values that we obtained, objects of the same style are going to have similar feature values, and they're going to migrate to the same cluster. So here, all the asphalt roads migrated over to this cluster. All the cobblestone roads migrated over here. And all the brick roads migrated over here. Once these clusters form, the centroid of each cluster is used as the exemplar for that style. So the centroid of the asphalt cluster would become the canonical feature value for asphalt roads. The centroid of this cluster would become the canonical feature value for cobblestone roads. So going back to previously, if we had a cityscape, we had an asphalt road, and we wanted to turn that into a cobblestone road, we take the canonical value for our cobblestone road cluster, and we substitute that value in place of the feature values we obtained in the image. So we kick out all the asphalt road feature values, put in the cobblestone road feature values instead, and when we give that input to the generator, the semantic label map and the boundary map are the same. The feature vector has only been changed in that way. Instead of getting the original image, we now get the original image with a cobblestone road instead of an asphalt road.
Yeah, so that answered my question, because here it's not just road, but road has different classes.
Yeah.
So you need to get some features. Okay.
Yes. This was to help facilitate the manipulation to change the style and appearance of an object. So next we're going to talk about, next we're going to just summarize this real quick. K-means clustering on a per class basis. Each cluster corresponding to one style, appearance, however you want to describe that. Make the centroid for each cluster the exemplar, and then substitute centroid values to edit object styles. Now we're going to talk about the experiments and results that the authors obtained. The authors performed two types of experiments, quantitative and human perceptual study. The quantitative comparisons worked like this. You start with the semantic label map and the other inputs that the generator would receive. You then perform image translation to obtain your output image. Afterwards, you take an off-the-shelf segmentation network and you segment that output, obtaining a new segmentation map. The intuition being that if you compare your segmented output to your input, if the image was translated well, those should be very similar.
But I mean, it depends on that. The original segmentation, this segmentation was obtained how? Like, is it ground truth or obtained by the first one?
Yeah, the first one was the input given to the generator. So you're given. So like when you train this model, you have a set of.
No, I understand.
Yeah.
But I'm saying, like, so this is given to the.
Yeah.
Input,
This is the ground truth.
But the question is, how did they get that? They did the manual, labels of each pixel, or they applied some algorithm to get the semantic segmentation.
That I'm not sure of. I would assume they took a bunch of pictures and just applied a semantic segmentation to that to obtain the set of labels that they used as input.
Yeah.
So I'd assume this is a segmentation of a ground truth image, and this is a segmentation of the translation of that.
Yeah, so see, the fair comparison will be that if they apply some algorithm to the image to get the semantic segmentation, and that's what input to the network, then when they get that image, they should apply the same algorithm. Then you can compare. See what I'm saying?
Yeah. They specify what algorithm they used at this step. I don't think they specified what algorithm they used to get this image.
Yeah.
So I don't know if they did that or not.
Okay, good. Yeah. Very good.
And here are the results they obtained. Compared against the Pix-to-Pix, Cascade Resolution Network, these are both state-of-the-art image-to-image translation frameworks, their own, and the Oracle here. So the Oracle here is just they took instead of performing the process that we saw earlier, they just took the ground truth image and segmented that. And so that was added as as a theoretical upper bound baseline. And as we can see here, their method obtained significant improvement over the existing state-of-the-art methods, especially in terms of mean IOU, and performed close to the theoretical upper bound, which are encouraging results. Oops, sorry, hit the button early. The other kind of test they performed was what they call human perceptual steady. This was performed in two variants, unlimited time and limited time. The basic framework of this study was that workers on Amazon Mechanical Turk were shown two images, either two synthesized images or a synthesized image and a real image, and were asked which one looks more realistic. It was the left to right ordering of the images was randomized to prevent that bias from affecting results. And as I said, this was performed in two variants. So the unlimited time version was the first variant. In this one, workers were shown two synthesized images, either synthesized by this method, by pix-to-pix, or by CRN. And they were asked which one looked more realistic, given an unlimited amount of time to scrutinize every imperfection in the image. The goal being to see just which image held up to close scrutiny best, who had the fewest imperfections. And this matrix shows the results. This test was performed both with and without the perceptual loss. And without BGG, this is the one without perceptual loss. And so what this number shows us is that our algorithm with perceptual loss was preferred over pix-to-pix 93.8% of the time. Without BGG, that improved to 94.6%. However, with CRN, omitting the perceptual loss actually hurt our results, which is interesting that it helped with one and hurt with the other. In either case, it was a 1% difference, so it didn't make adding that additional perceptual loss didn't make a huge difference, which seems reasonable given that it's very similar to the feature matching loss, so should be a significant degree of overlap to what they contribute.
So in this one, I mean, from this CRN is performing better than pix-to-pix, right?
Yes, because we did not prefer ours as often. I mean, admittedly, 86% didn't exactly perform like that much better. But still, yes, it was about 7%. 7% less often. We outperformed CRN. But we still got 85 to 86% preference rate over CRN, which again, these are encouraging results. The other variant of the perceptual study was the limited time. In this case, the users were shown two images drawn from the set of our synthesized image, CRN's synthesized image, or the real image. And the question again was, which one looks more realistic? This time, the users were given a limited amount of time, ranging from 1/8 of a second to 8 seconds. The goal of this study is to see whose imperfections jumped out faster. Given a limited amount of time, who had the more glaring imperfections? And at the 1/8 of a second, this line here corresponds to us being preferred over the other synthesized result. It wasn't really that great. None of them were that great. The real image beat CRN 60% of the time at 1/8 of a second. We beat CRN 53 or 4% of the time, something like that. So it was kind of a wash at this short of a time frame. As the time limit moves up to 8 seconds, our lead over CRN grows to being in the mid-70s. And similarly, the real image outperformed everybody. But it did not outperform us as well as it outperformed CRN, which again, encouraging results. When given a limited time frame, our imperfections didn't jump out as quickly. So in addition to the general results, just showing the performance of this framework against other frameworks, the authors also used those same kinds of tests to evaluate the contributions of individual components of the framework. So here is the generator comparison, where the generators used are UNet, CRN, and the coarse-affine generator. UNet and CRN being state-of-the-art image-to-image translation frameworks, image-to-image translation like generator architectures. This was the quantitative result with pixel accuracy and mean IOU. And as before, we outperform both of these results by 5 to 6% for pixel accuracy and by 30% in the case of mean IOU, showing that. And for these tests, the loss function and the discriminator architecture were kept the same. So it was this framework, but with the coarse-defined generator plucked out and with a UNet generator dropped in its place. So this is measuring how much did that generator architecture contribute to the success of the framework. And it's showing that there was a significant contribution from this generator architecture to the success of this framework.
So did they leave the 3 discriminators or?
Yes, so they used the multi-scale discriminator and they used the feature matching loss function. And then so they used then a UNet generator in place of coarse define, a CRN in place of coarse define, and coarse define. And so when you cut the improved generator out, results worsened, showing that this generator did have a significant impact on the improvement that this framework shows. And here is the same 3 generators, the same test with the human perceptual study. So here, when you gave it that same thing, this same framework with the different generators, the coarse-defined generator gave superior results according to human judgment, 80% of the time against UNet, 77% of the time against CRN. They also tested the discriminators. Here they kept the coarse-defined generator the same. They kept the feature matching loss the same. And they experimented with using the multi-scale discriminator versus just using the single discriminator. So here they just used D1. Here they used D1, D2, and D3. And they only gave a table in the results for the quantitative evaluation. But similarly, it showed an improvement in performance, not as much as the generator did. It's only 1% by pixel accuracy and 6% by mean IOU. So it did not have nearly as much of an impact as the generator did, but it did still have an impact. The results reported for the human perceptual study did not get a table, but they were mentioned in the paragraph. And I think it was 69.2% preference, which is not as impressive as the generator results, but still noticeably above chance.
Because see that here, they are in a way testing the discriminator, but they are actually looking at the quality of images.
Right.
Generator is generated. No? So better way to test whether the multi-scale discriminator works as you look at the discrimination, performance, how well the discriminators are able to discriminate. Then that will, I think, be more if you use multi-scale.
Right. So now we'll look at some of the interactive object editing that they were able to perform. So this is one of the synthesized images. We have an asphalt road, a black car, some trees, and some buildings in the back there. And these are some of the changes they were able to make by substituting the feature values. Here we substituted the feature values of the trees for some buildings. And we now have a car driving down the city, or in the city, instead of this green space. Here, we changed the car and the road to be a white car, a silver car, and a cobblestone road. And these changes were made just by taking that feature map, changing some of the feature values, and leaving the semantic label map and the boundary map alone. And similarly, when you put the discriminator, leaving the image alone. Thank you.
Okay, very good.